Hello. Okay, so we'll continue with our next talk in the Tools of Tomorrow track, and it will be on artistic content creation using a high-performance computing center. And the speakers will be Anne-Kathrin Baumann from the High Performance Computing Center in Stuttgart, Dr. Ari Hayuma from Filmakademie Baden-Württemberg, and David Körner from Hochschule der Medien, Stuttgart Media University. Please welcome them.
For the nice introduction, and also thank you to FMX for having us today. In the Tools of Tomorrow slot, we are talking about high-performance computing for artistic content creation. And as Volker already mentioned, this will be a three-splitted talk, so I'm happy to be here with my colleagues who will give you some insight on their research, while I'm giving you a short introduction to high-performance computing. So obviously, we're starting with what is high-performance computing? So if you want to know if you have a high-performance computer, just ask yourself, did I pay more than 50 million euro? So this is a quote that I hear quite often because it comes from the director of the HLRS, where I'm working. But it's not really saying much about high-performance computing. So I was looking for a more general definition. And I came up with this here. So high-performance computing most generally refers to the practice of aggregating computing power in a way that delivers much higher performance than one could get out of a typical desktop computer or workstation in order to solve large problems in science, engineering, or business. Well, you probably could have come up with that only by reading high-performance computing. It's a computer with a high performance, so that isn't that much of a surprise. But it is, in fact, more or less the definition. So I'm trying to say more about what are high-performance computers and what are their architecture. So they are just very cost-intensive, problem-specialized clusters of computers. So they are composed of the usual elements. You just have like normal computers, like processors, memory, disk, operating system, but more of everything. So it's just bigger. So what makes them special? Oh yeah. So the individual computers within such a cluster are called nodes. That knowledge will come in handy later. And those single nodes have a very special interconnection. So it's not just a lot of computers bound together, but really the interconnection in between them, the MPI. So they can communicate and, well, solve problems together very fast. Well, high performance. And they usually run with Linux or Windows. I'm also trying to differ it a bit from cloud computing. So this is high scalability computing. Cloud computing. We probably all know the different commercial providers as Amazon, Google, Microsoft, and they are like the public cloud. So everybody of you can just go online and reserve several nodes from them, and they will just give you what you ask for, so it's on demand. But they have just this normal interconnection in between the nodes, so it's just they connect a few computers, and that's it. The difference to high-performance computing, which is, by the way, used synonymously with supercomputing, is that we are more of a private cluster. So we are mostly national research centers. We have one continuous location, so we know where our computers are. If you go to Amazon or Google, you maybe can set the region, but you don't know for sure where really the nodes you're rendering on are. And of course, the difference is our special interconnect. So why am I telling you this? So we have here in Stuttgart the High Performance Computing Center. We are part of the University of Stuttgart, so we are operating one of Europe's largest HPC system, not only running the computer, but we're also teaching and training students, but also industrial users. And of course, we're doing a lot of research in the fields of HPC. Right now, we have the Hazelhand cluster. Well, it's a little pet name for our computer. It's worldwide number 14, if you compare it with the other supercomputers, and it's the fastest in the European Union. Right now we have a peak performance from 7.42 petaflops, and as you can see, it's just basic Intel Haswell CPUs, but a lot of them. So if you all add up, we come up with a total number of cores of 185,088, so pretty much. But why am I telling this at FMX? So there was the Be Maya movie a few years ago. This was a cooperation with the Mark 13 studio here in Stuttgart. And it was about the rendering of more of the half of the stereo images of the Be Maya movie. Why did we do this? So Mark13, they just realized that they won't make their deadline if they will run the renderings with their normal in-house clusters. So they came to us and we started this collaboration. And it actually worked out quite fine. So there had to be some pipeline adjustments so that they can render at our system. But it was really working well. So all in all, it was a win-win situation. So Mark13 met their deadline, which is quite nice if you want to have the movie in the cinema. And at HLRS, we had a new collaboration with a new field of industry, but also we could increase the degree of capacity utilization of our cluster. So, and because this project was such a success, there was the after the B process. So we have this ministry here in Baden-Württemberg, the Ministry for Science, Research and Art, and they said, hey, this is exactly what we want. We want more collaborations between research and industry. We want to push this kind of collaborations. So they got together different project partners, as there is the HLRS, what I told you just about, the ZKM, the Center for Media Technology in Karlsruhe, which is more an art museum thing, and the Filmakademie Baden-Württemberg, you all know it, and the Hochschule der Medien here in Stuttgart. So those 4 project partners came together and started the Media Solution Center Baden-Württemberg, which is a project that all of us are working in right now. So what is the idea? The idea is what I just told you. It's just technology transfer in between research and industry in the fields of VFX, media, art, and animation. So we want really to cover the whole field. So not only animation, but also the art sector. That's why we have the ZKM as a partner. Always, of course, with a focus on the usage and appliance of HPC. So we're doing research in the mentioned fields. My colleagues will tell you more about the outcomes of that research in a few moments. And we're also doing the preparation of the funding of a registered association. In German, it's a Verein. So if you come up with a better English word, please tell me. And we will carry on in this association the aims of the preparation project that we have right now. We have a website too. So to give you more of an idea of the abstract thing that we are doing, I came up with a little scheme. So on the one side, there are the media companies, artists, researchers, developers, and they have maybe ideas, questions, or any kind of problems. And we want to be the kind of bridge to the whole world of HPC. So we are having these different sectors within our project, which is, of course, the supportive research and development, because we're doing research and development ourselves, but also giving workshops on this topic, for example, at TechTalks, and I will tell you about that in a second, but also just consulting. So if you have a problem with HPC, or you can think of a problem which can benefit maybe from HPC, you can come to us and we will tell you about it. So this fulfills the bridge to the other side. So we are hoping for new synergies, new cooperations, and yeah, we will just be the bridge. One of those bridge activities that we have are the TechTalks Stuttgart, which are a biannual event series that we started this year. And it's kind of a small FMX on one evening, but with a technology focus. So it's about research and production in the fields of animation. Also with just short keynotes. Obviously, we are inspired by the TED Talks. That's why we chose that name. So we can also already save the date for the next Tech Talk, which will be on the 11th of October at the Theaterrampe here in Stuttgart. So this is one field that we are covering in the Media Solution Center, are the Tech Talks. And now my colleagues will tell you something about the research they did in the fields of HPC and media, which will bring me to my dear colleague, Ari Hayuna.
Thank you, Anne, for the nice introduction. So I'm going to talk to you today about high-performance computing for artistically directable simulations. Right. So as opposed to Anne, who comes from the HLRS, or the supercomputer itself, I actually come from the Animationsinstitut at the Filmakademie, which all of you probably know, so I'm not going to sing its praises, but I just copied them from the Wikipedia, it's right there. One of the important things, though, to remember is we do host the FMX conference, so you're welcome. And another thing which people don't necessarily know is that we are actually active in research and development. So we have a small R&D department that does work on several different projects, one of them being this one, the Media Solution Center project. So what is it that we do in terms of this MSc project? Well, let me introduce to you Palander version 1.0. So this is the prototype I have been working on. The long name would explain more about it. That is the Blender add-on for directing artistic simulations on a supercomputer. We're going to use that name, but it ran into some acronym issues. Okay. So I know what you're thinking. Palander, you know, everybody knows the famous Finnish alpine skier, Kalle Palander. He's actually the most successful Finnish alpine skier. You can see how many medals he won at the Olympics. But no, it's actually, the name comes from the two different parts that I have used to compose this prototype. So it's a prototype for fluid simulations that uses a content creation GUI, actually a DCC tool called Blender. And the simulation engine that we use externally is called Palabos. So you take half of each word and you come up with Palander. Both of these are open source softwares, which is nice in this project because, first of all, it's customizable. We get the source code, and if we need to change it, we can do that freely. But the biggest issue, because we use this on a supercomputer, is that there's no licensing issues when running it on a multiple nodes. If we would use a commercial software, we would need to have a license for each node separately, and that would be a waste of money, maybe. So we have actually published this code. It is available on GitHub at this address right here. I welcome you to download it and try it out for free. And make it better, please. So, why would we want to use Blender? As I said, it's open source. It's available freely at this address, blender.org. It's actually a viable competitor to commercial DCC tools. It has won at least one award, this famous award, Jury's Choice Award, at the SIGGRAPH last year. A wonderful short movie about a strange guy and his magical washing machine. I encourage you to watch it. It's also available for free for viewing online. Blender has its own fluid simulation engine. It's called LBeam. It uses the lattice-Boltzmann method as opposed to particle-based methods. This is a grid-based method. The name LBeam comes from just that, lattice-Boltzmann method, LBM, LBeam. Very creative. Right, in addition to Blender, we also use Palabos, and it's also open source, freely available at palabos.org. It also uses the lattice-Boltzmann method, which is nice because then we have an easy basis for comparison when we do simulations with both Blender's native engine and Palabos. The difference being that Palabos has been parallelized using MPI, or message passing interface, which means that we can use it on the supercomputer with more than one node that is in distributed memory applications. And the software has actually been tested by its manufacturers on a supercomputer in Switzerland on up to over 16,000 cores. So it's huge. Right, so when we put these two together, we get the Palander interface. Looks like this. So this is your basic Blender interface. If any of you have used Blender, you might recognize it. But it's quite similar to other DCC tools. You have in the middle this scene setup that you can modify as well. What you have now see here is a water simulation going through some makeshift trees. On the right side, you have Blender's own simulation with its own parameters. What's important is the left side. That is the Blender add-on, Palander. It has its own set of parameters that complement Blender's own parameters. But the prototype actually takes parameters from both and then passes them on to the simulation engine with this button. It says execute locally, if you can see it. That means that if you have this Palander prototype or the Palabos engine itself installed on your local computer, you can do a test run on your local computer, which is nice. But if you really want to do it powerfully, you can do send to cluster, which will send it automatically to the HLRS supercomputer, if it's set up right. Right, and what do we get then? Well, why would we want to use this then? That is a very important question. I will just go shortly through this. So you see, this could be one task right here, like a fluid simulation task. It's nice and small. It fits into one computer. But some tasks are too large. Now you see it doesn't fit inside the computer anymore, so you have to do something about it. But what you can do is you can parallelize it. You can do that to any software, but it's mostly useful for simulation software. What it means is you make a grid where every individual piece is as big as something that you would be able to run on your desktop. And then you take these and you send them to multiple cores for processing, like that. You see now they fit nicely into the cores. And then you retrieve the results and put them back together. So this is particularly useful for simulations, physical simulations like atomistic simulations, which I used to do earlier. But the film industry is more interested in fluid simulations. So why is this useful? It's because there's a high number of mostly independent events happening all over the volume. What I mean by mostly independent is, say you have a crowd simulation. Right here is one guy, bumps into his neighbor. The neighbor is going to feel it. So there's some interference going on between the nodes. But this guy over here is not going to care. He's too far away to sense anything. So there's some independence between things that are happening far away, even though some messages have to be passed back and forth between adjacent nodes. What's important to know is that this parallelization actually happens both for processing power and memory. So it's not only going to be faster, but you can actually use bigger setups because it's a distributed memory thing, and each core has its own memory equivalent to the memory of a single computer, which then adds up to a huge amount of memory, which is not available on a single desktop, which would only have something like this. Right. So to compare how they perform, I made this nice graph with L-beam as green triangles and Palabos as red spheres. So we increase the resolution of the simulation here on the x-axis, and the time required on the y-axis increases as we increase the resolution, of course. There's more vertices to be calculated, so Blender just exponentially goes through the roof. And at a certain point, there's going to be a memory problem. It's not all going to fit in the computer, and it crashes. So you can't even run something as big as that with Blender or any older solution that uses just your desktop. Whereas with the Palabos on a supercomputer, we stay fairly level here. I mean, the time required stays fairly much the same as long as we keep adding nodes. So we add computational power to take care of the problem that it would take longer and longer. So you stay within a reasonable time frame, and you have more of a chance to meet your deadlines. So other things that compare, there's also physical accuracy, which is better with Palabos because it's actually an engineering tool. It's being used in engineering applications worldwide. So if it's able to give you physical constants or measurement units, then it's also able to look exactly like nature would look with proper rendering. And the other thing, as I mentioned with the memory, if you add resolution or memory requirements, L-beam is going to crash because it's on a single desktop, and memory will run out. Whereas Palabos, with its distributed memory and an increasing amount of nodes, will just have an increased detail, which is really nice when you want to do something production style. So let's look at some increased detail. Here's another view of the water simulation we had a while ago, this time rendered by yours truly. I'm not an artist, I'm just a physicist, but I think it still looks nice. So let's see it a bit closer. You can already start seeing that high detail causes bubbles to form, and there's foam at the top, and it looks kind of almost ocean-like. Not quite there yet, but we can still increase the resolution from this. And all these bubbles and foam effects are actually just a natural cause of having such a high resolution. We didn't add anything to the simulation. So that is the big point here. So now for something actually animation-like, we have some students who have made this nice story about a beaver, which is going to be actually next year's FMX trailer. There's a beaver right there, say hello. So he is a nice guy who gets into all kinds of trouble. There's 6 different trailers of him running away from various things. And I will show you our interpretation of it, which is when we have this water simulation, the beaver will run away from the water, like so. So, how do I run this now? Just click. Yes. Yes. It's quite short, but let's see it again. Okay. So, to conclude my part, so the summary is that I have actually constructed a working prototype for something that is physically accurate high-resolution simulations that use only a fraction of the time required if you would do the same thing on your desktop. Of course, you still have a high computational cost per se if you say core hours, because you have a lot of cores, but very few hours. So in terms of clock time, you're still doing pretty cool. All of the software is open source, so there is zero cost, and there's no licensing issues when we run it on the cluster. And as I mentioned earlier, the source code is actually available on GitHub, so feel free to download it and use it to your heart's content. In the future, we still have some plans how to make this even better. We can implement other fluid simulation engines. There's the possibility of using particle-based engines, which would be even faster than the Slattice-Boltzmann grid-based one. So of course, there's less physical accuracy, but that doesn't seem to be a problem always with the film industry. And of course, we can also do a commercial fluid simulation engine into this, but there will then be the problem of having to distribute the licenses. It's not impossible, it's just impractical. We are actually collaborating with a local CGI company here in Stuttgart, so there's that to look forward to. We are comparing notes about how they can produce as nice a scene as possible, and then we try to achieve the same with our prototype in just a fraction of the time. That's still ongoing, but we have some promising results already. So that's it for my part. Now we move on to rendering, and David.
Thank you very much. So in the third part of the talk, we'll be talking about interactive remote path tracing using the HPC cluster at the HLRS. And the idea basically was, the motivation, let's see if we can use the HPC cluster to improve typical media production workflows, such as look development and lighting of a scene. And the approach was just implement basic proof of concept and see how it works. That's what we did. So the outline is, so we have this proof of concept implementation, which I'm going to be talking about, and it consists of three parts. The first part is kind of a back-end rendering application, which is running on the cluster, on the compute nodes, and then there's a front end at a remote location, which could be like a studio or some freelance artist, and then there's communication between the back end and the front end. So the artist makes changes to the scene, and the cluster is continuously rendering images of the new scene. So first I will be talking about the rendering backend, and then I will talk about the communication between backend and front end, and at the end I will be talking about the front end a bit, and I will also finish with some conclusion in this part. So before I go into the details, just let me show you the result of the proof of concept implementation. So here you see the front end. We used the browser, JavaScript web application, which we developed, and the cluster is now rendering continuously the images of the scene, and these images are streamed to the front end. So this has been at a remote location at home, and the cluster is currently running here on 30 nodes, and each node has 24 CPU cores. So altogether, this is now using 720 CPU cores. And the front end allows to select basic scene elements and change the parameters, such the camera parameters in this case here. And that's, yeah, the idea of this proof of concept is really to just show lightweight scene edits being done in this way. And also here we have this case where we change the lighting of the scene from a daylight scenario to a nightlight scenario. And you can remove lights, add lights, and change the colors. So that's what the demo video is showing here. So now here I'm adding a light source and try to make it look like try to make it give like a candlelight atmosphere. So I changed the colors, and yeah. No, that's a recording. That's a video recording. Yeah, but it has been live. That's a video recording of a live session. So, so now we're talking about the rendering backend. So first, we had to choose a renderer, and of course, we don't want to write our own render. So of all the different options, we had to go out and find the one which is suitable for us, and we had some criteria. First, we wanted it to be open source. For two reasons. First, we wanted to be accessible for companies and for collaboration, so licensing issue should be as minimal as possible. And second, we wanted to be able to go into the renderer and change it if needed, because we have like this interactive rendering idea, and there may be changes to do. Second, we wanted to be able to do interactive distributed single frame rendering. So this means we wanted a single frame to be rendered using multiple nodes and at an interactive frame rate. We wanted to have good node level performance, and by this we mean that each individual node should be used as much as possible. So we wanted ideally to have each single node be multi-threaded and also use vectorization. And also we wanted to make use of this HPC interconnect which has been mentioned. So the HPC cluster, as was mentioned, has high throughput, low latency interconnect, and we wanted to make use of that. And ideally, the render should be production-proven, just to make it more appealing for like industry. So we finally settled with OSPray. It's a renderer engine, a rendering or ray tracing engine, which has been developed by a group at Intel. And you can find more information about it on ospray.org. It has been published, I think, 1 year ago or something. And OSPray can be understood as Intel's answer to NVIDIA's optics framework. So if you know optics, it's like a generic ray tracing framework where you can use it to do path tracing, but you can also do like sound simulation or many other ray tracing based applications. So it has really a wide range of applications. But OSPray is different. So OSPray is kind of Intel's answer to that, but it's actually, OSPray is primarily or only, it's been exclusively developed for scientific visualization. So that's basically what OSPray is being designed for. But interestingly enough, in scientific visualization, we currently have a trend that more and more there's this use of physical-based rendering. So modern scientific visualization uses path tracing and physical cameras and physical lights and so on, because the reason is that the visualizations look more appealing and also like make it easier to see like characteristics in the data sets. So here you see it, a visualization rendered by OSPray. There are streamlines visualizing some flow or something. And the nice thing is that we have all these, with this we have all these basic building blocks in place, like with Monte Carlo integration, physical cameras, physical lights, physical materials, that we can actually do light transport simulation as well. So OSPray hasn't been designed to do that, but it's a side product that you can actually do this. And this is why we used it, because OSPray has been designed for high performance computing in mind, so it uses MPI and everything. So it's not production proven because it's not meant for media applications yet, but it still ticks all the other boxes. It's open source, it does interactive distributed single frame rendering, it has good node level performance by using threading building blocks to do multi-threading on the single nodes, and also uses ISPC, which is Intel's vector compiler. So it takes C code and turns it into vectorized code, vectorized binaries. And it uses HPC interconnect by using this mentioned MPI, this message passing interface. It's an API which allows you to use different high performance interconnect libraries such as InfiniBand, OmniPath, and in our case on the Cray here at HLRS we have the HLRS interconnect, and MPI is an interface to that. So the backend application altogether looks like this. We have multiple nodes running on the compute nodes. We have worker nodes, and then there's a single head node, and all those nodes communicate via this Cray areas interconnect. And the head node talks to the outside world by using standard TCP/IP transfer protocols. So now I will talk about the communication, because here we have actually quite an issue, because the compute node and the client is not allowed to talk to each other. And this is for two reasons. First, for security reasons, and the second reason is that the scientific computing, it's basically like the idea of the application is you take a problem, you put it on the cluster, then you run the problem on the cluster, and then you look at the result and eventually download the result. So this is, and in our use case, we kind of deviate from this typical HPC workflow, so to say. And we worked around this by exploring the fact that within the HLRS network environment, the compute nodes can actually talk to other machines. So we installed, or we wrote this little proxy, and this proxy is really just relaying information from the compute nodes to the clients and vice versa. And when the proxy is talking to the compute nodes, we use 0MQ. It's a C++ library for doing distributed applications. So it takes care of messaging and everything. And when we talk to the client, we first use an SSH tunnel to go through the firewall. And on top of that, we have a WebSocket. We use WebSockets when we talk to the browser front end. Or we could also use 0MQ to talk to other standalone C++ applications. So now we'll be talking about the front end. So the front end, as you've seen, is like JavaScript web application running in the browser, and it's only really meant to do lightweight editing. So we just wanted to see, can this work, and how does it work, how does it feel like? So we only can do we can change parameters on objects and stuff like this. And it receives compressed images from the backend for display. And the architecture of the web application is inspired by 3JS editor, which is open source. And our architecture looks very similar, but we cannot use WebGL and because our images are rendered on a remote location by a different renderer. And this brings us to an interesting problem because we found that distributed interactive rendering applications, they kind of challenge actual today's scene APIs. And before I talk about this, just let me clarify terminology a bit. So when we talk about the rendering API, we mean like a set of functions which we invoke on a renderer to produce a final image. And on the other hand, we have a thing called scene API, and this is also an API which has a set of functions, and this defines the scene we want to work with on a higher level. And it's usually associated with file format storage. So, and the application ties these two APIs together. But in our case, when we do interactive distributed rendering, we kind of have some requirements on this API. And first and foremost is that the user input, so when we have a live session and the user changes the scene, we want these changes to the scene be the same as if the scene would be loaded from disk. So changes to the scene should be handled by the API the same way as we load a scene and vice versa. And further, we want the scene API to be able to work in applications where we have multiple renderers. So consider a renderer which takes proxy geometry from the scene and renders it to a display. And then at the same time, we have another renderer who is producing high-fidelity images using progressive path tracing or something. And we want the scene API to support these use cases easily. And further, for us, we have this on a separate. We have a renderer on a different location. So ideally, the scene API takes also care of. Excuse me. Takes also care of the network problem that we have to transfer. So by this I don't mean that the scene API should do the network communication, but changes to the scene in one place should be easily be able to propagate to other locations. So we looked at two popular scene APIs. First, universal scene description, and this is really a really nice, strong API. And on the Google Docs, Google forum. We learned that they are currently rewriting part of this API to make use cases like we have much more easier. So they are in the process, and I think in the near future this will be a really good API to do things like we just did with our interactive path tracing. But at the point where we had to make the decision, it was quite a huge development effort to use USD, and therefore we shied away from this because the development effort wasn't justified by the small use case we have here. And the second API is a nodal scene interface. It's proposed by 3Dlight, and it's really appealing because it's very lightweight. It's meant for interactive applications. It's kind of missing this distributed part, but it's a really nice concept. But at this point, it's just a specification, and the development status is kind of unknown to us. So there wasn't much we could work with. So what we did is we wrote something very simple, which is inspired by a nodal scene interface and was extended with remote procedure call thing. And here's just some code to see how it looks and feels like when, to the developer. So the client sees these functions, and this looks very similar to the nodal scene interface. And these functions, they don't do much. What they do is they basically take the parameters and turn it into a binary representation, this command structure you see here. And then these command structures, you can basically store them on disk, but you can also transfer them to another location. You can use them locally. It's kind of like a fine granularity representation of your scene. And on the receiving side, so if you send this over the wire, and on the receiving side, you have this iScene interface, and that implements these functions. That's done by the application. And then at the bottom, there's this execute method. And it takes the scene interface, and it takes the binary commands, and you just execute the command on the scene. And this way, you can like distribute changes on the scene very easily across different locations. So that covers the front-end part. And now, as an outlook, I want to just mention there's some things we still need to solve. First is how to integrate such an interactive application into today's scheduling systems, which are primarily batch-based. So that's an open question to us. And also, we would like to have a platform. So currently, the prototype is some shell scripts and SSH login stuff. So ideally, we want to have a Python script which takes away all that effort, similar to established cloud services. And of course, the use case is really just showing a small set of what could be done and could be tried. So maybe there's a lot of points we could also work on in this case. So to conclude, we have seen interactive path tracing using just CPUs on the cluster using OSPray. And also as a side note, it's interesting also to do development on the HPC cluster because it allows you to get a sneak peek into the future of many integrated core architectures like Xeon Phi. So if we here run on 30 nodes or 100 nodes, this is going to be in the near future or midterm future, this is going to be something which will be available on desktop computers. So the future kind of is you have a little cluster on your desktop computer. So here you can kind of assess what this will be like. And with that, I hand over to Anne-Catherine to wrap up.
Thank you. Yeah, I just wanted to give a short wrap-up, so what we just heard and listened about. So HPC, what I gave you a short introduction, is not only for scientific use. We're actually experiencing nowadays an opening of HPC to all kinds of industries. So it's not only for the automotive industry, but also can be used by media industries. So, and obviously, we also had some first use cases and special applications where it was shown that there is some point in using it, which also was proven by the research of my colleagues. So HPC is a viable alternative to established cloud providers for some applications. And with the project that we have started, I think there is a good bridge in between research and industry. And with that, I just wanted to thank you for your attention. And if there are any questions now or in the future, I think we're happy to answer them. Thank you so much.
Yeah, thanks a lot for that insight into the MSc project. Questions from the audience?
So about the rendering, I don't know how much control OSPray offered you, but I was wondering if you could talk a little bit about the way that it gets partitioned amongst those cores, whether you're doing kind of iterations with random seeds or if you're actually tiling the image, and any experiments or thoughts you might have about what is the right way to do that.
Yeah, currently this OSPray just tiles the image in image space like it's typically done, but the group is also working and has some stuff in place. I haven't looked at up in detail, but they do data parallelism. So what OSPray is also good at is rendering volumes and services at the same time, and then they have some strategies for splitting up the data to different nodes, because in scientific computing you have these huge data sets, and I'm not sure if this is applicable for rendering and visual effects, but it's certainly something which we can look at and will look at to see if it's useful for rendering large data sets in you have in typical media productions. But I didn't talk about OSPray in more detail because here it's not that I'm saying OSPray should be used or something. It's just the renderer you chose. What I found surprising is that all the other renderers out there, they don't use MPI. They just have standard TCP/IP stuff for doing distributed rendering. And so I'm kind of curious where this goes. And yeah, maybe at some point we will see like Arnold using MPI or something, I don't know. But this is interesting. There was also this V-Ray prototype, and they had there was this construct movie, and the V-Ray was used, and they had set up V-Ray on a cluster, and they used InfiniBand interconnect because they had the same issue where they had to use a low latency interconnect. So I'm certain that the renderers will be more like they will take some of the stuff, but how exactly I don't know. Yeah.
Hello, thanks for the presentation. I'm not familiar with HPC, so I have quite a naive question. What is exactly the difference between high-performance computing and just a big render farm? So what is really this MPI in terms of hardware and software?
Yeah, so this is a tricky question, and because in my experience, to be very honest, I think there is not so much of a difference. You can see some if you look close. So we have mentioned this interconnect. So I'm not familiar in detail with other render farms, but for example at Amazon or something, they don't have InfiniBand. So you have interconnect means that instead of having like a network card, the connection to the CPU between CPUs is plugged directly into the PCI Express slot. So it's directly on the bus basically. And that's the key difference. So the CPUs are able to talk together to each other much faster. So if you have so something we want to shy away from is to use this as a render farm, because a render farm is really, the standard clusters are really well suited for that. So you have a lot of machines, and each machine takes a frame and renders the frame. So in this case, you don't need high performance interconnect at all. But if you have a big problem which a single node cannot solve alone, like if you want to render a frame which a single node cannot render because of memory limitations or because it just takes so long, then you need to think about splitting the problem really into different parts, and then you want to have a good communication between the nodes. And then there's also other differences because, so for example, on the high performance cluster, we don't use virtual machines at all. So you exactly know what hardware you use, and this can be a benefit. So if you know exactly what hardware your node will run on, then you can be much better at optimizing it. And that's why we don't see any images or any virtual machines used at HPC. Another difference or another aspect which is good, is important, for example, if you have a commercial provider, then your data center will be like far away. So for example, here in Stuttgart, the closest Amazon center is in Frankfurt. And this is okay if you do rendering or something, like batch rendering, but if you want to do like interactive like stuff where you need a good connection, then it actually makes a difference if your data center is close or not. And so for the industry here, it's actually an important point that we have a strong connection to a data center which is close. So that's what HLRS is providing. So I would say these are kind of the key differences.
More questions? Again, maybe continue.
Yeah, next. Yeah, thank you very much. The rendering aspect, especially like interactive rendering, goes more and more for in terms of GPU, and you're like I think just provide like CPU mostly. Like, is there a benefit to especially like using mainly CPU besides like of the harder distribution into GPU, which like you need to find out the pinpoints, yeah.
Yeah, I really love this question. Although I don't really want to go into this discussion between GPU and CPU because this is so messy. I have no clue where this is going, but I can say some words. So first, this comes back to the question: why is Intel writing like a ray tracing engine? And the reason is that in scientific computing, all the HPC clusters are dominated by CPUs. So if you solve a problem, you have a lot of CPUs, and then once the problem is solved, you want to visualize it, and then you need a GPU cluster if you want to do GPU rendering. So they say it totally makes sense to make use of the CPUs, even if they are not as fast or not as good for rendering interactively as GPUs are, we still want to make use of the resources because scientific computing won't be done on GPUs primarily in the near future. So that's one reason to make use of the resources, and I can see similar ideas maybe in media production where you have a lot of CPUs clusters. Sure, renderers are moving maybe towards GPU, but I don't know. So I mean, Arnold is in the making, the GPU version, and there's Re-Ray RT. But so I have no idea where this is going. But there's a lot of CPUs, and I don't see them to go away completely. So it makes sense to use them for rendering as well. And this comes together with the problem of data location. So the nice thing is that Filmakademie is doing these simulations, and they are on the cluster. It's big data sets, right? So you don't want to download them just to render them locally on your GPU farm, because downloading them would, for big data sets, would be just take massive resources. So you want to render them remotely as well. So that's another point which kind of speaks for CPUs. But I have to admit that this interactive rendering, so you need a lot of CPUs to match one GPU. So that's still true, yeah.
But does it make it a difference for simulation-wise? Because it's for interactivity, like all the render try to do it, but for example, for simulation-wise, is there a benefit to use CPU, or is it also like going to GPU in this way? So yeah.
I think the answer is pretty much the same as David says. So there is no inherent benefit to using CPU, but so historically, physical simulations have been done with CPUs, and GPU is fairly recent development. And it's not being used in the scientific world as such, as far as I know, to such a big degree. Again, since all the supercomputers are basically CPU-based. But there are some new simulation engines that are run on the GPU, and they do show some promising results, like they can do real-time, fairly high-resolution simulations on the GPU.
Okay, there's one more question in the back.
Yeah, so the other question I had is more about how is the technology evolving? Is it becoming more affordable? Do you have any guess at how the pricing is going to evolve? Or if there are other centers opening with HPC installations? Do you have a guess about it?
Yeah, well, as far as I know, I never heard of other supercomputer centers who are doing this kind of effort towards the media industry. This is also a very special thing, even for Germany in our center. So this is an initiative that comes from our director, because he doesn't only see high-performance computing for scientific use, but also for different industrial use, and really sees the benefits of such cooperations. To the pricing, I can say that it's not cheaper or more expensive than the usual render farms, as we are some kind related to the state. So we have to keep the prices. We can't do dumping prices because our computer is already paid for, because we are not allowed to influence the market. But it's not more expensive or cheaper than other render farms. So I don't see any kind of price developments with supercomputers, but as I said, I think the collaborations are coming.
All right, that was very interesting. Let's thank the speaker one more time. Oh, that's another question, yeah? Okay, all the way to the back.
Hello, thank you for your presentation. How do you deal with scene distribution overhead between different nodes? Because it's probably, I can imagine that it could be more interactive when you use a few nodes than when you use really a huge amount of nodes. How do you deal with this overhead? Thank you.
Yes, so scene distribution is a problem. So there's another scene which we wanted to get to work, which is like a forest, dense forest, and it uses a lot of instancing, and loading the scene takes a lot of time. It doesn't work yet because the data has to be distributed between all the nodes. So that's a practical example that it is a problem, and there's no easy solution to that. So all nodes need to get the data to render the scene. So that's definitely something where it would be nice to get like more or better algorithms to deal with that.
Right. Thanks a lot for your interest, and in a few minutes we'll prepare for the last talk of the track, 360 degrees video to 360 video to 6 degree of freedom conversion. So let's thank the speaker.